This is a quick tutorial on how to compute standard deviation. One thing I want you to notice at the beginning of this is that, as we've talked about, the standard deviation, or standard deviation in general, is a descriptive statistic. That is, it describes the data that you have at your disposal. It is the most popularly designated variation measure, so it's meaning it's the most reported measure in journal articles. So you want to know it and generally understand what it's showing you. What it's showing you is the level of dispersion in your particular data set. So what I'm going to give you is, I'm showing you how to do it twice, and I will show you one set of data we'll be looking at is right here. The second set is below it. So you can see that there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 in one. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 in the other. And you can see that if we just do an average or the mean, if you look up here, Av equals average A6 through A15, that gives you the mean. And similarly down here you get the average A22 through A31. So now the question is, how much dispersion is there between these two? They have the same mean, so which one has more variation in it? And I think just by looking at the data, you can see in here data that runs between 5.4 and what's the highest number in here? Is it 6.6? So between 54 and 66 is the range. Whereas in here you have 4 to 100 and you have some widely dispersed numbers. So intuitively you should know that your standard deviation for this particular sample will be larger just by looking at the data. Now, the way you actually calculate it is starting with by looking at how far each data point falls from the mean. That's the big kind of issue. No matter how you're calculating it, that's what you're trying to think about. That shows you how variable the data are. So we would take each data point and subtract it from the mean. So, for example, 4 minus 61. 4 minus 61 equals, in this case, negative 57.2. 100, the second data point, minus the mean of the set. 100 minus 61.2 equals 38.8, and so on. So just to give one more, 6 minus 61.2 equals negative 55.2. You go through each one of them and then you square them. So for example here, as you see in the way that this has been created, F6, which is this value here, times itself. F6 times F6. That's the square of the difference between that data point and the mean. The square of difference. Then once you have all the squares of differences for all the data points, you add them up. And this is what's called the sum of the squares. So you can see the sum of the squares is the sum from G6 here all the way through G15. Now, excitingly, we get to variance, which is, again, one of the well-known descriptive statistics on variation. Now, what the variance is, it equals the sum of the squares divided by the number of data values minus 1. The number of data values, if you remember, is 10 minus 1 equals 9. So it's 20,777 divided by 9. And you can see here, I put into the formula bar, equals G16, right here, divided by 9. So the variance is 2608, and the standard deviation, I believe that most of you know, is the square root of the variance. So I put, ta-da! Now, one alternative is to simply use Excel. And you can write in its equals standard deviation, STDEV, for A5 through 14. And I'm sorry, I needed to change that. I must have moved the data around. So it would be A6 through 15. There we go. So that would be correct. And what you would come up with is this same number here. Now, okay, let's go down. So notice this is a lot of variation right here. And one thing to remember, again, one thing that you can do with standard deviation is start to figure out where most of the data will lie. So remember that 68% of all data fall between one standard deviation below and above the mean. So what you're really looking at here is 61, the mean, plus 48, and 61 minus 48, and that's going to give you the general level of where the variation, 68% of the data fall. So let me just do it on my calculator. 68.2 or 61.2 minus 48, just to make it simple. So that's 13, 2, and then 61 plus 48 equals 109. So 68% of all the data will fall between 13 and 109. It's a pretty big range on the basis of that standard deviation. Now let's go to this data set. Again, looking at this, far less variability. So we already know that the standard deviation will be much smaller. We do the same thing. We take each data point and subtract it from the mean. And how did I do this? Sorry, I made a little typo here. This should be 61. Okay, so we start with this data point. 61 is the data point minus the mean, 61.2, equals negative 0.2. 60 minus 61.2, that must be what I made the error. I must have moved the 61.2, oops, 1.2 equals negative 1.2, and so on, all the way down through each data point. You square them. So this number is 0.2 times itself. 1.44, not surprisingly, is negative 1.2 times negative 1.2. Then you sum them to get the sum of the squares. And remember that to get the variance, you divide the sum of the squares divided by the number of data points minus 1. So in this case, it will be 105.6 divided by 9. Which is up here, you can see in the bar. So the variance, ta-da, 3.42. And then standard deviation would be the square root of that. Oh, excuse me. I'm sorry, I moved this down here. So I knew I was screwing up something here. So this is the variance. I just highlighted something incorrectly. Okay, so this should be no fill. So this is the standard deviation right here. And I put again, ta-da. So the variance is 105.6 divided by 9, and then the standard deviation is the square root of the variance, 3.42. And once again, alternatively, instead of calculating this, which is what you'll do going forward, is you simply plug in the standard STDEV, and again, I must have moved something and not corrected it. And in this case, it is 22 to 31. And that is how you would come up with the exact same number. Now, what's really important is that you notice again, notice how much smaller 3.42 is from 4.8. So you could see that in this case, 68% of the data will fall roughly between, we'll say, 58 and 64. So it's a much, 68 and 50, let's say, 58 and 64. 68% of the data. Look at the difference there on the basis of the standard deviation, what we can figure out. So notice that the standard deviation conveys that there's much more variation in sample 1's data compared to sample 2's data. And it's just a good way to help us understand data. So, for example, you're trying to figure out how much variability there is in in a particular set. And I used the example the other day in one of our voluntary meetings. If I were an executive coach, as were you, and say we each had 10 clients, and our clients were administered client satisfaction scores, essentially asking how good we are as executive coaches on a scale of 1 to 7, 7 being outstanding, 1 being terrible. And if we both could average a 4, but maybe I had a much smaller standard deviation than you did, meaning I'm pretty consistently a 4. So let's just say kind of average. I'm good, but I'm not outstanding. Versus you might get, say if you had a higher variation or grander deviation, you might have a range between 1 to 7, and maybe most of your data are somewhere between a 2 and a 6. So in some cases, your clients think you were very bad, and in other cases, they think you're outstanding. So it's fodder for people to think about what is important, to evaluate important sets of data. I hope this helps, and I'm going to move on to another one.